Hello, so today for Lab 7 we're going to be looking at systems of nonlinear equations. Let me make this so I can move the mouse. Okay, there we go. So there are only two techniques this time, so that's, fewer choices. The first of these is Gauss-Seidel, which we've looked at before, so that's our successive substitution technique. It doesn't always work, so there's the downside. But at least, it's easy if it does work. Now, one of the things that a lot of people missed on the exam and still applies on this is that what you need to do is, like, if you have A, B, and C values, you start with a guess. You then calculate a new A value, for instance. Once you've done that, you replace the old A value. And you keep doing that all the way through. Each time as you calculate a new one, you replace. So that it's always a new set of values. You're always updating what you're substituting in. Okay, so be sure that you do that when you try Gauss-Seidel. The other technique, which is the more reliable one, is Newton-RAPHSON. Now, it's a lot more reliable, but it's also harder to work. You have to actually do calculus. Okay, it's just derivatives. So it's not all that hard. The rule says that we're going to take the first derivative of the function with respect to each variable in turn and organize them in a matrix format. So here we're doing just two variables with two unknowns. And our problem we're going to look at today, it's going to be 7, but don't worry about it. It's not that, that's really just not that much more difficult. So we're going to do that, and you're going to do that for the first function and then for each function subsequent to that. Just make sure that what you took the derivative with respect to, they all get lined up together. All right. That is going to be evaluated at your current guess. Okay. We're going to multiply that times xi plus 1 minus xi. So our new values minus our old values will be this column here. And that is going to equal to the value of our function negative evaluated at our current guess. Okay? So I'm going to tell you right now the things that commonly go wrong is people either forget to do the negatives. Okay, that's a common one. Or they forget that what you're calculating here is going to be a delta x, right? It's the difference between our old and new value of x. Okay, how are you going to solve this? Well, this is always going to be linear. Okay, so therefore all I need to do is find the matrix inverse here, multiply it by these negative functions evaluated at the old value, and that's going to get me my delta x's. To get a new guess, all I do is add my old guess, and that gets me my new guess. Okay. Now, we're going to be doing this to solve a problem. There are a lot of nonlinear systems of equations we could choose, but I wanted to do something about fluid flow. So we're going to do a pipe network problem today. And I use these kinds of problems all the time, or use them, run into them all the time, because I do a lot of work with Engineers Without Borders, and we are constantly providing water to communities. And when you do that, you've got to take water to various branches of the community, right? People don't live in neat little rows. They live on streets that turn off of each other. So therefore, we end up with these pipe networks. So this is a fairly simple-minded pipe network. And the idea here is that the pump is going to send water through a pipe until it reaches a branching point. Some of the water will go this direction, some of it will go this direction. And this pipe is going to flow till it reaches another branching point. Some will go this way and some will go this way. But this joins back in here. And so this and this combine to make this, this and this combine to make this, and will flow on into the tank, whatever's left. Now notice this particular pipe network doesn't have a lot of extra, like a house over here, so some water's being withdrawn. Trying to keep this pretty simple. I would work a problem like this for, say, EWB, because we are trying to make sure that our system will provide water to all of the homes. Because you would hate for there to be a system where, okay, these homes all ended up with some water, but there was never enough water in the system to provide water to the people that lived on this branch of the pipe network. So therefore, this is a very practical kind of problem. When you do the analysis, there are basically two different types of equations that we're looking at here. And the first is balances on each node. Now a node is where you have a T in a pipe, in this case. So node 1 is where stream Q01 comes in and streams Q12 and Q13 come out. Now if there's no accumulation, a material balance says that in minus out is going to be 0. And so we get Q01 minus Q12 minus Q13 is equal to 0 for this one. And we can go through and do that for each of these various nodes. So here I've got 1, 2 coming in, 2, 4, and 2, 3 coming out. At node 3, which is down here, I have 2, 3 coming in, I have 1, 3 coming in, and I have 3, 4 coming out. And on node 4, I have 2, 4, and 3, 4 coming in, and 4, 5 coming out. All right, so that's my first 4 equations. But I have 1, 2, 3, 4, 5, 6, 7 unknowns, so I need 3 more equations. So the next 3 equations are going to be done based on pressure drops. Now, if you can create loops or places where you know what the pressure is, you can write an equation. So for instance, if I started here at point 1 and went all the way around this loop and added up the pressure drops for each one of these, that pressure drop, by the time I got all the way back to the beginning, would have to add up to be 0. Because, right, the pressure at a point is the same in all directions. So therefore, the pressure drop from 1 to 3, and the pressure drop from 1 to 2, and the pressure drop from 2 to 3 add up to be 0. Now, because the flow rates are defined with the direction, we end up with plus and minus signs as shown here. Now, there's one weird loop, which is loop 1, and loop 1 is saying that if this started at the atmosphere and this started at the atmosphere, then this could be connected and form another loop. And so that's what this last one here is. It's a loop around the entire system. Okay? Now, it does include the pressure drop across the pump. That's going to be a pressure increase. Everything else is a pressure drop. The pressure across the pump would be something that you would know. No, not known. Okay, so now then we have all of these delta P's for each pipe segment. How do we figure those out? Well, you learn more about this in some of your other courses, but it's basically proportional to the flow rate in that pipe squared times a constant. Now this constant isn't truly constant, but it is relative to the friction factor. We've looked at the friction factor before. So the friction factor we know changes a little bit with the Reynolds number, which relates to the flow rate. So if the flow rate changes, that's going to change the friction factor, but we're going to assume a constant value in our problem. So if we do this, I'm going to figure out Kij for each pipe section. Kij will be different. Okay, so I'll have to calculate a Kij for this part, a K12, a K23, a K24, right? I'm going to have to calculate those for each one, but it's based on the length of the pipe, the density of the fluid, the friction factor. The number 32 just pops out because of all these relationships. Pi squared and d to the 5th, the diameter, the inside diameter of the pipe. Okay? Those constants times Qij squared are going to be the delta P's I put in here. For the pump, that would be, again, a known value. Now we're doing this so that we can apply Newton-RAPHSON. So for the first equations, it was just like Q12 minus Q23 minus Q34 or whatever. I don't remember the subscripts. When you take those derivatives, it's either the derivative of that one with a positive 1 in front of it or a negative 1, or it doesn't show up in the equation, in which case the derivative is 0. So you're going to get all your entries for the first 4 equations be 1s and 0s, negative 1s and 0s. For the second set, go back and look, I've got k times q to the second power. If k is constant, then this is going to be 2k times the q. And so I'm going to have that for that, or 0, for my various terms for the last 3 equations. Okay, so that's going to allow me to set up the Newton-RAPHSON. And there's a handout that is on the Canvas assignment page. And I want you to just simply work that problem and see if you can calculate the Q values. Now they should all turn out to be positive. The signs are assumed, so therefore you should end up with positive values for Q. If you do not, then that's a sign that you've done a calculation incorrectly. Okay, so that's it for the video, and if you have questions, let me know.